Thanks. Can you hit the little thumbtack up there? Thanks. I think the batteries are dead, Kevin. Oh, wait, no. Okay, there we go.
Okay.
Yeah, it's good.
So our first speaker today is Kai Van Horn. Kai received his BS in multidisciplinary engineering from Purdue in 2007 and his master's in electrical engineering from U of I in 2012. He is currently a PhD candidate working with Professors Sawyer and Alejandro Domingos Garcia. So the title of Kai's talk is Measurement-Based Real-Time Economic Dispatch. And I'd just like to say I think Kai may win this semester's, if we had a presentation title award. It's a really cool title. So it's just very, very well said. So
well, thanks, Chris. I appreciate that. It's a good note to start on. Huh? All right. Well, as Chris said, I'm going to talk about measurement-based real-time economic dispatch. I'm kind of going to give an overview of the market system that we have in place, and then talk about where this fits in that. So I like to start with this map of the United States showing, or the North America, excluding Mexico, that shows the independent system operators, ISOs, and the regional transmission organizations, RTOs, that are tasked with operation of the grid. So they're tasked with maintaining reliability and economically balancing supply and demand on the grid. And you see their geographic coverage is not universal, but they do actually schedule around 2/3 of the US load. And so that's why this real-time dispatch actually is important, because 2/3 of the US load is being scheduled using processes such as using market processes. So these ISOs and RTOs, they run various market processes to balance supply and demand on the grid, to procure ancillary services, which are reliability products such as spinning reserves or regulating reserves that allow them to maintain reliability even in the face of outages that might occur. And also to form prices that are used to settle the supply and the demand on the grid. So when people are purchasing electricity or selling electricity, the prices at which they are compensated are determined in the markets. So the general structure of the market, of the markets that we have a multi-settlement market system where we have forward markets that operate generally the day before, such as today, for tomorrow, where today we'll run a market that schedules resources to meet the forecast load tomorrow in each hour. And then when we move into tomorrow, the operating day, then we'll have real-time markets which then rebalance what the realizations of the load and the resources are and any outages that may have occurred in the interim, so that we have then economically meet supply-demand balance and meet the reliability requirements that we have in place. We would also then reprocure ancillary services and such things. And the prices that are formed and that are settled in day ahead are different than the prices that are formed in real time. And that's part of the whole theory of why multi-settlement works that I won't get into here. But basically what we're focusing on here is the real-time market, because that's where all the uncertainty in the system comes to bear on the market processes. That's where any undetected outages would impact the prices that are formed and the dispatch targets that we have for resources in the system. And that's where the load that must be served is actually realized, and it's no longer just a forecast load. And the main tool that the ISOs and RTOs, the main tools that they use in order to undertake these market processes are the security constrained unit commitment, which is basically which units should I have turned on, because some generators take a long time to turn on and we can't just turn them on when we need them. And the security constrained economic dispatch, which is how do I best use those resources that I already have on. And the problem that they solve is a market clearing problem. This is a very general problem, and it's applied in many markets around the world. It's basically just the maximization of social surplus, which is if we have a supplier of some commodity here, electricity, and they have some willingness to supply, some incremental willingness to supply. So like if you pay me, if I'm supplying you PG, and you pay me, then I would want to be paid lambda. And similarly, some incremental demand where they're saying if you pay me, if I'm supplying or if I'm consuming PD, then I would want to be paid lambda, or I would want to pay lambda. And we are trying to find the point where we maximize this this triangle here, which represents the summation of this consumer surplus, which is this area, and the producer surplus, which is this area. And basically, in general, this can be reduced to the minimization over generator cost. So maybe it's helpful to think of it in that way to be more clear. But more generally, it's the maximization of social surplus. And then we have constraints in this optimization problem, which are physical constraints. And that's the power balance. We have the network flow constraints. And we have equipment limits, like generator limits. And then security-related constraints, which might represent ramping or n-1 contingency constraints or other reserve product constraints that we have. And then the main outcome of this market clearing process, or this market clearing problem, are the resource dispatch targets and those locational marginal prices. So those locational marginal prices are really important, so I'm just going to give them a little extra time right now. These tell us basically the, let me go back one. So in this market right here, we have, so the market clearing would be where these two incremental demand and supply curves cross. And this would be the market clearing price for this market. Lambda would be the market clearing price. And in this case here, this would be the case where we don't have any binding flow constraints. We would have a single clearing price. But if we have any binding flow constraints or other constraints in the market, then we can have LMPs that are not the same in the system at each point in the system. And in that case, we would basically have this problem solved at each node. And then we would have a different price at each node. And so that's why it's called a locational marginal price, because it tells us the cost to provide the next megawatt at each bus. And it's typically decomposed into three components. There's an energy component, which doesn't depend on where you are in the system. It only depends on how you specify the slack bus or the multiple slack buses. There's a congestion component, which depends on where you are in the system. Basically, it's incorporating information about when I want more megawatts at a particular location, how's that going to impact any constraints that are binding? So if I have a congested line and I want a megawatt at bus I, how is the procurement of that megawatt going to impact this line? Because we can't overload that line. So we may have to redispatch units in the system. And so that's the congestion component. And then you have the losses component, which is basically how do the system losses change? How do the losses change when I request an additional megawatt at bus I? And so you can see kind of that we have these delta LK, delta P losses for a change in output at this bus I. So this kind of is very suggestive of how this LMP calculation depends on sensitivities, further motivating like what we're going to be talking about here. So these sensitivities are for the line flows and for the losses are very important. And I'm going to focus in this presentation on the injection shift factors, which are flow sensitivities. So these are very important because they provide their sensitivity of the change in real power flow to the change in injection at a bus, that making the assumption that that injection is withdrawn at the slack bus. So we inject at bus I, and we withdraw at the slack bus. So how much of that injection flows over line LK? That's the injection shift factor for line K with respect to bus I. And using this, and so these are typically calculated in the conventional formulation using a DC system model. So that's a linearized representation of the power system. And so we have now this model-based real-time economic dispatch. So we're still, like the market clearing problem, maximizing the social surplus. We have our power balance constraint. And then here I highlighted in orange these constraints that depend on the injection shift factor. So these model-based network constraints, which would be based upon the injection shift factors that we calculate from a DC network model. And we have security-related constraints, which also depend on those injection shift factors. And so the way that this kind of works is that we have telemetry, which is like SCADA data measurements out in the system. We collect those measurements. We fix our network model, which may have changed since the last time we did the economic dispatch if we had a breaker open and we got information back about that. We perform a state estimation using that system model and the measurements that we have. We calculate our model-based sensitivities, and we formulate our real-time economic dispatch. And then we solve that real-time economic dispatch and calculate our LMPs, and we have our dispatch targets. So, this is all fine and good. So just as an example, this is MISO's economic dispatch process. You can see up in the top left here we have the network model, the state estimator solution, and the constraints going into it. Here we have some information from the day-ahead market, because the economic dispatch basically is, like I said, is optimizing around a previous day-ahead solution, what we thought the load was going to be and what it actually turns out to be. And then it generates the dispatch targets. So this is all good, but this all depends on a model of the system. We're assuming what all of those parameters in the system are, that we know what they are. We're assuming that we know which breakers are open and closed. And furthermore, typically we only really care about, we're really focused on the system that we are operating. So consider this internal system here to be MISO. Say this is MISO here. And then this is everywhere else. MISO doesn't perform its economic dispatch with a model that is a detailed model of the entire US electricity system. They have a simplified representation of everything outside of MISO. And so the external system has a lot of uncertainty in it as a result of that. Like, what if that model they're using is just not very good? And so this, all of these uncertainties and all of these inaccuracies, they are manifested in the outcomes of the real-time economic dispatch. The problem is solved with respect to this data, and so the outcomes we get will be impacted by those inaccuracies. So just as an example, suppose we have, take the 9-bus WEX system, and suppose you have that a line in the model is assumed to have an impedance of 1.2 Z, but it's actually Z. So we thought that it was 20% higher than it actually is. And then we solve the economic dispatch. So there's a hash line here underneath the squiggly line, and then a dotted line below that. The hash line is the economic dispatch solution with the quote-unquote good data, the actual data. And the dotted line is the economic dispatch solution with the bad data. So you see there's a difference between these. And it's about, I don't know, maybe 60 cents here, which doesn't seem like a lot, but we're clearing thousands of megawatts. So this can add up to a lot. And not only that, is that what this basically says is that the apparent congestion that we get when we solve this market is actually less than the true congestion, which is not a good thing, because that means that a line in the system could be overloaded when we thought that it wasn't. So this inappropriate price signals that are sent that could be caused by inaccurate model data can have significant economic impacts and even reliability impacts. So what we want to do here is to formulate the real-time economic dispatch that depends only on measured and estimated quantities. We don't want to have anything in there that's based on assumptions about parameters in the system. And then I'll demonstrate the outcomes that we would get using that approach with some case studies. So phasor measurement units are really what makes all this possible. The key component of those devices, since they measure voltage, magnitude, and angle, and then also they can measure power flows, is that they have time-synchronized high-frequency measurements. And so when we have time-synchronized high-frequency measurements, it enables us to use measurement-based operational tools where before we may have an assumed system model. So the way that this works for the sensitivities is this. So you imagine you have a system and you have all your lines and you have all of your injections. So say we measure our line flows and our injections. And then we assume, OK, so just like in general sensitivity analysis, we say, OK, let's say there's a linear relationship between a particular line flow change and all of the injection flow changes. And then we can write this linear equation that relates basically what we already defined as the injection shift factor, the sensitivity of the line flow to the injection. We can write the change in flow on this line as a sum of the injections at all the buses times those sensitivities. And then if we collect these measurements over time, then we'll have a set of measurements that are all at each time step is time synchronized across all the points in the system. We can use this then to estimate what these linear factors are. And if you're really interested in this process, then I suggest you read Christine Chen's doctoral dissertation. She just published that about this, and she has a lot of great papers about this too. But I'm going to build on top of this, so I'm not going to go into great detail. I just wanted to give you a general overview. Professor Plow?
Just to clarify, Are you assuming that you have one PMU on every line?
Yeah, we're assuming we have a line. Here we're assuming we have a line flow measurement, yeah, for all lines. Mm-hmm.
Is that a good assumption? I don't know.
Well, I mean, I think for some smaller systems it could be. And as we move into the future, perhaps. At the moment, we definitely don't have full coverage, like in MISO, for example. Yeah.
Do you know what coverage we have right now online?
I don't know. I don't know, yeah. That's a good question. Yeah, yeah. So another thing to think about too is that generally when you formulate the market clearing problem, you don't care about what's happening on every line. And when you estimate these linear factors, you wouldn't need so you wouldn't need to estimate them for every line. So you wouldn't need measurements for every line. Yeah, you would only really care about those lines that are like often overloaded, and so you want to, because they don't constrain each line in the market formulation because it would take forever to solve it. Yeah. So there are a lot of ways to reduce the number of PMUs you would need. Yeah, and Christine also covered some of that in having fewer than full coverage. Yeah. Okay, so once we have estimated these injection shift factors, we can then reformulate the real-time economic dispatch. So instead of having model-based network constraints, we can use measurement-based network constraints. And similarly, we'll have measurement-based security-related constraints. And then our process becomes this. We process our PMU measurements. We estimate our measurement-based sensitivities and formulate the problem. And then we solve it, and we get our real-time economic dispatch targets and our LMPs. So the benefits of this is that, again, it does not depend on a system model. We're instead using measurements to estimate these sensitivities. It can adapt to the system conditions if something changes. Even if we don't know it changed, our measurements are going to pick that up, and it will be incorporated into the market clearing problem. And I think another great strength is that it fits into the existing real-time market framework. It doesn't require that we make a fundamental change to the way that the markets are already conducted. It basically just uses more appropriate information to formulate the constraints in the market. So to demonstrate this, I'm going to present a couple of case studies. We're going to look at undetected line outages in the 9-bus and the 57-bus system. Just as an overview, I looked at the LMPs in those systems, so the prices at every bus, and I compared the estimated LMPs with the DC LMPs. So the DC LMPs are the LMPs that would be calculated with a linearized system model. The AC LMPs would be the LMPs that we calculated with the full nonlinear system model. That's the closest to the real LMP that we can really get. And so I took the mean of the mean squared error of the LMP difference at each bus, and that's what I'm showing here. It's kind of like an aggregate view of the system. And so this AC versus DC is the AC versus DC LMP. So this is basically a measure of how good the DC approximations are in that system. And then the estimated versus the DC is how close our estimated LMPs are coming to the DC LMPs that we would calculate with the system model. And the estimated versus the AC is how close to the true LMPs are we getting with our estimate. And so I think it's interesting that that our estimates versus AC and versus DC are both less than the AC versus DC here. So it's kind of like our estimation is falling between the AC and the DC LMPs. And also that on the 57-bus system, that the DC approximation kind of sucks. It's not so good. So first, we're looking at the 9-bus system. And so here we have 3 generators and 3 loads. We're going to let there be an undetected outage on line 5. And we're going to constrain line 3 to 15 megawatts. That just makes it a lot more interesting when you have different LMPs at all the buses. And the total load and the generation are reported up there. The relative cost of each generator is at the current loading point is what's shown on there. So the LMPs I'm showing here for black, the pre-outage model-based LMP. So that's the model-based LMP if we didn't detect the outage of that line. If we didn't know that line was on outage. The pink is the outage or the post-outage model-based LMP, which is the LMP if we did know that line was on outage. And then the green is the measurement-based LMP. So those are the LMPs calculated with a measurement-based real-time economic dispatch. So I mean, I think it's pretty clear when you look at it that one, that when you don't detect a line outage, the LMPs are significantly impacted. Which do you have a? Oh, sorry, these are DC LMPs. Yeah, I'm focusing on DC LMPs since that's what they use in the market clearing. Yeah. But I'll mention those AC LMPs later because I think they actually do, they have an important role to play here. So there's enormous difference between the pre-outage and the post-outage LMPs, which it's exaggerated in the 9-bus because it's like a ring. So if you remove a line, then basically, if you have a congested line, then everything goes to 2 different prices, and so it can change the price a lot. But what to notice here is that the LMPs and the measurement-based are very close to the post-outage model-based LMPs. So we're getting, with the measurement-based approach, very close to what the LMPs would be if we actually knew that outage happened, and then we solved the market clearing problem. And then another important, oh, Raj? Oh, why is it slightly different? Because it's not, we're not getting exactly the same injection shift factors as we would with the model-based approach, because there is some estimation error. Yeah. Yeah. But there's some question about whether or not those injection shift factors are better or worse, because they may incorporate information that the DC injection shift factors can't incorporate. So they may actually be better. So this might be better LMPs. But so the generation dispatch is also different because, of course, we have a line that's out that we didn't know was out, and that's going to change all the flows. And what's important about that is that the generation dispatch determines the flow pattern in the system. So particularly on line like line 7, where initially the flow was like minus 130, and then if we didn't detect the outage, our line flow would shoot up to, or if we did, yeah, our line flow would be increased by a lack of that detection. And so we could potentially have an overload on a line because we didn't detect this outage. And that's a serious reliability issue. So then looking at a larger case, just since that's kind of the 9-bus is kind of a toy model. Again, we're comparing the model-based with the detected outage and the model-based with the undetected outage, and then the model-based with the detected outage and the measurement-based. So on this system, we're outaging one line, and we're also constraining one line so that we have LMP divergence at the buses. In this case, we again have that the measurement-based LMPs are closer to the post-outage model-based LMPs. However, you see that they're slightly higher. And what's interesting here is that if you plot on here also the AC LMPs, the measurement-based LMPs fall between the DC and the AC LMPs for all of these buses. And so this was also a case where on this test system, remember that the AC versus DC LMP difference was quite large. So that indicates that the DC approximation is not very good, and that the actual prices of the AC LMPs are difficult to achieve with the DC LMPs, and that we're getting closer to that with these measurement-based LMPs. This kind of suggested that there's additional information encoded in these sensitivities. Again, the generator dispatch has changed, and we basically have a similar thing. There's another case here on line 6, where you have a small flow if you don't detect the outage, but when that outage actually does occur, you have a really large flow on that line, so it can be dangerous. So just to conclude, this measurement-based approach to the real-time economic dispatch does offer some enhancements to the conventional model-based approach. It enables us to form appropriate price signals and to get dispatch targets that won't lead to potential reliability issues. It also is adaptive to changes in the system and can deal with erroneous model data. And there's some question, I have some question myself about whether it more accurately reflects the AC conditions. So I'm going to look into that, investigating the causal factors of those observed market outcomes. Why are those LMPs as they are? And also, I want to implement. I'm working right now on implementing the measurement-based security constraints, because with the security constraints are dependent twice on the injection shift factors. So if that model data is bad, you actually get hit twice. And so the dispatch you come to could be severely impacted by incorrect model data. So we're going to look at just how bad that might be. And then, as I mentioned, with external versus internal system, I want to also look at how this could be applied in that context, and how much better the results you would get would be if you had measurement-based sensitivities in your formulation as opposed to some model of the external system. So I'd like to acknowledge the Granger Foundation, who supports my research. And with that, I'll take any questions you guys have. More. How? Oh, so real-time economic dispatch will take, well, typically economic dispatch takes place on a 5-minute basis in markets today. So, I mean, I think that it should fit into the same framework. It should have the same requirements as existing economic dispatch. Yeah.
Yeah, because if that's the time scale, then like all the state estimator and all topology processing have faster time scale than that, right? So,
Correct, yeah. But we're not doing any topology processing.
yeah, but what I mean, like, how do you see, like, using, like, because if you use the topology and also the estimation, you can do the AC, full AC, OTR.
Oh. So I think typically in real-time economic dispatch with contingency analysis and stuff, they don't use full ACOPF. Maybe for a subset of contingencies that they need to get a more a finer grained like view of. But the full ACOPF takes too long to run in real time, and so almost all of it is done with DCOPF, yeah, with just some offline studies done with ACOPF. Yeah. Yeah. Any other question? Yeah.
So the whole point, the things we're discussing here are like line outages, but we're assuming we have all the lines in this case. When you were doing it, you had all the line flows. So you kind of would have detected an outage because there would have been the zero if you wanted
on your PMU data. Yeah.
Right. So, but you envisage being able to do all this with just congested lines, just the congested line flows. Would you get a very similar result? You just said.
Yeah, well, I mean, the injection shift factors actually don't matter if the line flows, if the line's not congested,
right?
Because they're not going to cause binding constraint.
But you could do the whole subset thing, have not all the line flows.
Yeah.
Do the same process.
Yeah, because.
For your formulation, you don't need it.
Yeah, you would still need the measurements of the injections at the buses, because basically each line has a set of sensitivities for each injection, and so however many lines you want, you need the sensitivity of that line to the injections. So if you want to just monitor 10 lines, then you just need 10 line flow measurements and then the injection measurements. Yeah, and if you had fewer injection measurements, then that would hurt the accuracy of your estimation. Matt?
So my question kind of follows Roger. So you said that the whole supply demand is a two-step process, one day ahead and one real time.
Mm-hmm.
So your tool is a real time part, right?
Yeah.
So kind of same what Raj said. So if you do have the PMU data, but you're not feeding it back into real time and market, you still know when the line's out. Right? You're not going to install PMU and then not look at the data at all.
Yeah.
So the kind of delay between seeing a line out and then factoring it into real-time market. Yours is doing it real time.
Mm-hmm.
What kind of delay do they use if they are not using it?
Yeah, so actually it's very interesting. I try to answer this question myself about how long it takes for them to detect a forced outage. And the way the market rules are written, it basically says that please, if you detect a forced outage on your system, one of the market participants, please inform us within 60 minutes. So it's actually, yeah, so actually, I mean, maybe it would be great to talk to someone who works in operations and get a more clear answer to that question. And I've been asking that question around anybody I can get my hands on. But it hasn't come to me like that there's a very sophisticated way of dealing with that. They rely largely on the market participants reporting those detections. All right. Thanks, guys. It does work. I think I was maybe just not pushing it hard enough, but you can. You probably don't. I was using it a little bit because I thought that wasn't working, but it appears to be.
Okay.
But if you want it in case the battery goes out or something. Oh yeah, thanks.
Do I actually need this? Should I put it here? Right here is fine. Thank you.
You can just drag it onto the disk.
Okay, let me, as soon as I know, regular view is probably the best. Okay, that one. Perfect. Oh, well, he has to go first. Yeah, I guess, yeah, go ahead,
Okay,
start.
our next speaker is Ladi. Ladi gave me permission to just use his first name, part of his first name. In 2009, Ladi obtained his bachelor's degree in electrical engineering with a focus in control systems from Clarkson University in New York. Ladi is a joint degree, one of 2 students at U of I understand, who's doing a master's in electrical engineering and an MBA. And the focus of Ladi's electrical engineering master's is power system analysis with practical applications to the sub-Saharan African scenario. So with that, thank you for your presentation, Ladi.
All right, well, in light of time, we'll try to breeze through some of this really quickly, but please stop me if you have any questions. I'll start off with just the motivation for my work. How do you go forward? Perfect. The statement there is it hits home. Sorry. Oh, go back one. Good. The statement there hits home because growing up in Nigeria, inadequate electricity access was a norm, and so I've actually grown quite fond of darkness. But really, I'm really motivated to try and support the energy development in the area, and that's why I'm conducting research in energy. Okay, what did I do? Yeah, that's it. No, sorry. So the outline, I'll just give a little bit of the context of Africa, go through some quick reliability analysis that I ran to give some more perspective, go into solar valuation, which is what I'm doing in this study, and a little bit of the preliminary results I have, and then I will close. So context, Africa, 54 countries, 1 billion people. A lot of development is happening across different sectors, including energy, of course. Billions of dollars in investment. The World Bank, European Union, et cetera, et cetera. One of the more important ones that has motivated me, technically, is Power Africa. And that was founded in 2013, USAID. And it's really huge because of, not just because of the amount of capital that they're driving, but really the partnerships that they have in place in the private and public sector. I have $21 billion there. That's U.S. government and private. So that's a lot of money. But relative to the U.S. and how much they use to maintain their grid, you can see it's a big difference. That's because the U.S. grid is so much more developed. Oh yeah, my research focuses on Nigeria and Ghana right now. I would like to do all 6 or all 54 countries, but I'm limited in resources. This was an interesting graph I saw in the Power Africa report, the recent report, 2014. And let me see if I can use this here. The red there shows the kilowatt hour per capita in each country, and the blue shows electricity access. And therein lies the disparity. But therein also lies the demand. Right? That shows there's a huge demand. Of course, in the African countries, the access, those with access still experience brownouts. And then that's part of why there's a need for development. I also further go on to compare US and Nigeria. Of course, all this is just to give perspective. 15 gigawatts of solar capacity currently. Germany has the most, I believe, 33 or so gigawatts. 0 solar in Nigeria, and this is the same in different countries. That's where there's a huge development effort in terms of renewables specifically. CO2 emissions. That one stood out, 17.5 tons per capita. And I checked what that meant in mass, and that's why I put that there. So, but this gives perspective. That's all I'm trying to do here. Also, in terms of irradiance, you can see the potential just visually, but my research is trying to actually do some sort of analytical study on what this means. But visually you can see, and I try to note the difference in the scales there. Red in Germany is very different from red in Africa or in the US. And yet Germany has the most solar capacity. So, done with the perspective side of things, I'm shifting into a quick reliability analysis that I did from a resource adequacy standpoint. And that just means, do we have enough generation to serve our load? But this was done based on a probabilistic framework, the probability of potentially serving your load. And it's based off of the idea of a reserve margin. So your generation minus your load is your reserve. And that's what I'm defining here. And so at a particular state is, you know what, let me just go into the example. So generation modeling, this is a two-state model with two generators, G1 of 30 megawatt capacity, 90% potential probability of having that 30 megawatts, 10% of not. You call that a forced outage rate, but it's really a probability, not a rate. And I'm just showing that in terms of probability density functions. So that's why it's a two-state. You can have a you can have a three-state model. You just have a third probability there with some capacity in between 0 and max. And then, so combinations of these generators give you all your possible states. And that's what I'm showing there. And the respective density function for that. And so you do something similar for your load. For your load, but when you do that for a load, you're doing it relative to the base load value and potential peaks from the base load. And that's what I'm showing here. This is, again, a simplified model for 1 day. 1 day of your load, you have 6 hours of the day at a peak value, assume it's 60 megawatts, and base load is a 10 megawatt value. Okay. And so from this, you then generate a reserve model. What I'm showing here, and okay, is this working here? I can't see it work, but I'll just move. Capacities and probabilities. Capacity of that is just 50 minus the 10. So available capacity minus load demand at that point. Probabilistically, of course. The probability of that happening is 0.54 because I just multiplied the two probabilities of the gen and the load existing at that time frame. And you generate your table. And the green there, if you see the key, the green is higher probabilities, green on the left key is higher megawatts in reserve, lower megawatts in red, and probabilities, green is higher probability of occurring, and white is lower. Well, white is just saying it's so low it may not happen type of thing. I hope this is clear. But what I did is I took this and I applied it to Ghana and Nigeria, but I just show you Ghana here. And this is the gen model for Ghana. Ghana has about 8 or so generators, key generators, a few hydro, a few thermal units. And this is what I generated for that. And a simplified model, of course, 2-state. And then I did the same for load data that I got from their transmission authority, Gridco. I sampled about 28 days, ran it for a whole month study. And that's what I'm displaying here. That's 500 and so hours. Go ahead.
Did the power authority in Ghana provide the availability for the generators?
Yes, I found that in a report, a Gridco report, yes. Availabilities, the lowest I think I saw there was about 60%. So yes, I did factor that in, exactly. But again, it was a simplified study assuming a two-state model for each gen. But good question. And so with that data, this is the reserve model I generated. Let me go back here. There are 3 levels of base loads that I've assumed because of how variant the data was. So I just said a lower value of a base load, a higher value, a mid value, and a higher value. And that's what you see there. And so with that, you see 3 cases, and you see it getting worse with increase in base load values. That picture right there really stood out to me. The red line is indicating the borderline of negative reserve values. And so that's why you have a lot of brownouts, you see, and my increased skill to see in darkness. But this was similar for Nigeria. This is the table of probabilities. And you can see, even though it's red, really red there in terms of reserve, the probability of that happening is really low. And so that's what this is showing. Nonetheless, based on those two graphs you're seeing, you would look for a region where you're in a negative reserve with a high probability of occurring, and that's where your concern is. But moving on. So how do you show improvement with this kind of model? Well, consider the case of incremental 100 megawatt upgrades. And what happens is you see the line pushes further out. So this was a base load. I just picked the base load value of 1544, that case. Increase add 100 megawatt capacity in some way. You see the line going further out and further out. That's how so this would be good, but you would hope it even gets more green, right? That's what you'd hope. And hence you see a value in increasing the capacity of your system. One thing I should point out is this whole model assumes you have perfect transmission to supply your load. And of course, that's probably not the best assumption, but for this case, we'll take that as is. So the question of interest is how weak or strong is the case for solar in Nigeria and Ghana and all these other countries? Beyond that, how do you actually value that, and how do you go about stating the value of that? And that's what I'm trying to study in light of course, all the trends we've pointed out here. And so I assume 100 megawatt solar capacity upgrade. And I say, let's take 2 cases. You can implement this in form of a small scale type of distributed PV or a utility scale, just one large PV case. And 100 megawatts, again, is just an assumption. And what we do is, apply valuation metrics, what we call levelized cost of energy. That is just a cost per megawatt hour over the life of the entire project or the entire resource that you're dealing with. And you compare these against each other just to get the cost of energy itself is a metric, but the comparison against something else is what gives you even more value. That's what we're trying to do here. These metrics are primarily based on the idea of time value of money and net present value. And I'll briefly explain these 2 things before I move forward. So time value of money simply states money today is worth more than money tomorrow, because of the uncertainty of tomorrow. That's a simplified way of explaining that. And so there's a discount rate to price the risk of waiting for tomorrow. There's a discount rate. That's what it's called. And then net present value is just, well, I'll explain present value first. Total discounted cash flows. Assuming you're going to get a stream of income over time, you discount it each year compoundingly. That's and you sum that up. That's what your present value will give you. But now the difference of that from your cost, your initial cost at year 0, is what you get as your net present value. And that's just what that expression is showing. And so that's the fundamental idea behind levelized cost of energy and all these other valuation metrics that are being used here. And so in the process, I get input data and I just try to get some sort of energy revenue, potential energy revenue of this 100 megawatt DC plant in both cases. And then I get the cost of doing those things in both cases. And then I get the output metrics from whatever I calculate. And that's the overall process. And this is some results on revenue that I got. This is for Nigeria. I've done something in the background here. You see revenue each year, 10 different states in Nigeria. I couldn't do across all the states because I also thought of ability to pay and ability to do these things. So I picked 10 states with the highest GDP on the assumption that GDP is a good metric for economic welfare or well-being. Arguable as that might be, it's pretty well accepted an indicator. That is GDP. So that's what I used. And then I based on GDP percentages, broke that into potential for setting up this PV plants in these regions. And this is just for case one, just to point out. Forgive me.
What's the payment structure for power producers?
The payment structure.
Like how are they, what price are they paid at? For generation. Like you're calculating revenues, so basically you have an output, so what's the other?
Yeah, so this is the revenue, and you're asking about the price, the rate structure, that is.
So they're going to produce so many megawatt hours, and they're going to get paid some price.
Exactly. So the prices do vary depending on the class of generator you are, and I believe I checked for the commercial, it was like about 25 naira, which came out to about 25 divided by 170, assuming that was the exchange rate.
But it's fixed all the time, the same price.
But it's pretty much fixed, but of course they change it. And so now they're trying to get into more dynamic market pricing for such things, but for now it's just fixed. And of course I used prices for what they know currently. I mean, solar is not developed there, so the idea of pricing solar is not even factored in. So it was prices based off the current electricity system. But very good question. And then in terms of cost, this a big part of what I'm researching is this is cost of PV based on current US system, on the current US systems and projects in place. And you see it divided there across the different classes. But how do you apply this cost to the context of Ghana, Nigeria, and all these other countries? Will that be the exact same price, for instance, in Ghana, under the assumption that labor is cheaper? But then, will it actually be cheaper because are you manufacturing these solar cells in these regions? So will it be more then because of import-export duties? Those are the types of questions that I'm primarily trying to answer here. For now, I have assumed that labor is cheaper and I reduced the price by a factor of percentage. I believe I used 10%. but yeah, and so I factored the cost in. And voila, like magic, I get this. No, I do all the technical analysis, I factor in the NPV, and what I'm doing is I've broken it across 30 years, and you see this big drop in year zero because that's the initial cost. But now I have that bar there going up in year one what that is showing with an incentive in place. So a government incentive in terms of a renewable energy program. But then it keeps dropping. This is a preliminary result because I've seen that there are other incentives that I can factor in that may make this may make this a little different in terms of what I've gotten, but this is what it shows. I mean, payback right now is 0. There's no payback, and so it's just, like I said, just preliminary. But go ahead, Siming.
Why does the loss increase?
Very good question. With these kinds of projects, what you assume is that at life, there's some sort of salvage value, and you bake that in, and the salvage value being, if you have a generator, you probably can sell that and make some money off of it, even though it has gone that long, or something of that sort. And so when I add that in there, that's why you see that big jump at the end in year 30. It's a standard assumption, and I think it was at life salvage value of 10% off the cost of your project, or something along those lines. But that's a good question. Maybe I should set it to 0. Maybe everything dies off at the end of its life. I don't know. But yeah, I'm trying to do this same thing for case 2, but I put load in there. That's a joke. I need to still continue doing the analysis and get some results on that. And that's that. Further work, of course, like I said, finish off the required work for the case 2, and also apply this to other countries. Transmission analysis, like I said, the transmission lines are not perfect, are far from, in fact. And as you increase capacity, you need transmission, and so need to somehow factor that in. And in terms of research, I mean, the sky's the limit in terms of research, because it's in a stage of development. There's a lot that needs to be done, not just from the standpoint of applying what we know right now in power systems to the region, but also in terms of how best to, what's the optimal solutions for the problems there. And pick and choose market design, power systems analysis, and the rest. Acknowledgements, ITI, for taking their chance with me, and Professor Ogunnubi, of course, for his leadership. He pushes us to innovate all the time. And yeah, and the power group, you guys, I learn a lot from all of you. My family, and of course God. I'm a Christian. I have to thank God. So thank you very much. Any questions? Hydro project. Inga, the famous, Mr. Prosper can probably tell us about Inga. Oh, right. Well, you can share the Inga, the potential for Inga.
Essentially, is the project of Inga, which is where there is enough potential to power most of countries in Africa. But now they are talking most about the gas. Why America is bring 21 billion in Africa? There is a business, a good one. So there is a big discovery of natural gas to the eastern region. This is where is the most business work in Africa, with Tanzania, Kenya. Yeah, so
the potential is more gas, natural gas,
yes.
hydro.
We work to compensate to bring also solution to the global climate change. So let's use the natural gas. The problem with hydro in Congo, there is too much politics going beyond.
Yeah.
So you were
No, yeah.
So I had one question. You first talked about reliability analysis, which is basically the capacity value of resources. And you thought of, are you going to be incorporating the capacity value of solar into the benefits associated with the installing a solar facility, like the one you described? So certainly that would be that would reduce the levelized cost of energy if you had some benefits from the capacity being there.
Repeat that question, the last part. The last part.
So had you given any thought to incorporating the capacity value of solar?
Oh, into the reliability.
Into the analysis of the cost, into the cost analysis.
The capacity of solar. That's exactly what I'm doing here.
No, the capacity value. So so you talk about the reserve margin and the
Right.
ability of having insufficient capacity.
Uh-huh.
So the solar capacity it will provide additional capacity, but not, of course, the entire capacity is not always there.
Oh, so you're saying as an additional resource is
Yeah, yeah. Well, the capacity factor is not enough. Yeah, so you can reduce the LO.
the LLP.
EUE. Yeah.
Yeah, so that's where I was showing that improved capacity, be it from solar or any other resource, will improve the reliability. The loss of load probabilities were the regions under the red curve. Now, let me go back to that. Maybe I'm
What I'm saying is you were assigning like a
Mhm.
that he's saying, higher.
Yeah. Well, and also too that the 100 megawatts of solar is not the same as 100 megawatts of wind.
Ah, right. Okay, good.
Right. And so that's why levelized cost of energy is good, right? You can compare the costs of each of these different resources because you factored in all the elements that go into using that type of resource and come up with a levelized cost for that resource, and that's what you compare. You're right. I have just done this for solar, but what will, and I have some data from past work that was done to compare against a distributed diesel PV, not PV, distributed diesel setup, and that cost, and see what the pros and cons are. The thing about that study is it was done Africa, like across for the whole region. The problem with such a study is you lose the specific cost factors for like a particular country, and it might vary. It might vary a tad, especially when you start crossing these regions and you find out their systems are completely different. But yes, that kind of comparison in terms of the benefit of using natural gas versus solar still is a good one to do. Is a good one to do. I don't know if I've answered your question, and if not, yes, please. He raised his hand first, and go ahead. Yeah. So I will tell you, I used 5%, but that needs to change or vary. That's where a Monte Carlo analysis, and I put that in further work, needs to be done, because the discount rate is something that is up in the air. You have exactly, and the challenge with this is the idea of solar in these regions is new, and so how do you price the risk of that in these new regions? Do you do it against another region, or it's really hard to? But you do something relative, you do a relative analysis, and you use a value. But a Monte Carlo will really give a good understanding of, if it does vary by this much, then how does my result vary? So I really need to understand Monte Carlo and use it. A good question. Yes.
Your load data comes from something of like what load was, right?
What load was, well,
What data you used to do this?
yes.
But in reality, the demand is probably a lot higher. It's not served.
Good question. I think I have something on load data here. But I'm sorry. Yes, load data I used was current actually, but in the past, with this year.
Because you have all these brownouts, so the actual number is higher. So
Yeah, exactly. It's right. Okay. All right, that's it. Thank you.
Solar, like not just the cost of solar, because yeah, the reduction in the LLP has a benefit because the expected unserved energy times the cost of unserved load.
I see your point. I see your point.
Yeah, that's like the quote unquote capacity value of a resource.
Right.
The capacity benefit.
Oh, okay. Now, would that tie to benefit cost ratio?
That's really good.
Okay, that's good.
Yeah.
I thought I was moving too fast. I wasn't sure, but.
See, when I saw his slides, I looked at them and thought, yeah, they're about the right length for an hour-long presentation.